All right, coagers and field trippers. Pretty much anybody who was gone Friday, February, or not February, wow, Friday, December 5th. We left off on the 4th on question 15. So we're going to pick up on 16 for this video, and we're going to go through the end of the lesson. So for number 16, they show just this bottom portion of this graph. We need to mark the point on the graph where we would find krypton 91 and barium 142. So we're going to go over to 91-ish, and then up till the line. And that's where we would find krypton. Take a second, try 142 for yourself, please. All right, so when I do 142, I go over to like basically halfway between 20 and 60, a little to the right, and then I'm going to plot my barium. So when uranium splits, I'm going to move my captions. There we go. When uranium splits into barium and krypton, is our binding energy going to go up or down? Remember, it's more negative towards the bottom. There you go. For this one, it's going to, say it real quick. I feel like Dora. When this happens, their binding energy is going to decrease. All right. You guys can hear the construction. It's like the worst circle ever. Okay. When this splits, is this going to absorb or release energy? Well, if energy is decreasing, it's going to have to be released. If you're releasing energy, is this endo or exothermic? I want you to know that I'm dancing for you in my heart right now, and I hope that you're dancing along with me. This is exo because it exits. Okay? When energy exits the system, we have an exothermic. Go ahead, flip your page over. Let's take a look on page 40. I hate question 18. I'll be so free. I hate question 18. Basically, here's what I need you to know for 18, because this is also on the Google Slides. For question 18, how is the energy that was released causing a boiling water reaction? Well, energy gets released as heat. Heat boils water. So energy becomes heat, becomes boiling. Okay. When water boils, it makes steam. What's the steam used to do in this reactor? It spins a turbine. Which generates electricity. Like I said, this is all you guys on the week 14 slides. I do not expect you to know this for the test, but I every year forget to take this question off this packet. And to be honest, it doesn't hurt you to know this, right? We did talk about how this is called a boiling water reactor. There are multiple types of nuclear power plant, and boiling water reactors are just the ones that we're studying this go round. 19 is what I'm really concerned about. Let's look at 19, shall we? I actually think that there might already be a video of me teaching 19 on YouTube. It's that important. This is one of our energy graphs. So this is not the binding energy diagram we were looking at. This is one of our energy graphs like we drew in lesson 4. So this is one of our ones that starts with that like tipped over L. And on this one, we have our energy. Down here we have time. Okay. The balanced equation in 15 is the uranium equation. We've actually drawn this exact graph before. So if we think about it, during the fission of uranium, the breakdown of uranium, is it going to gain energy or is it going to lose energy? It's going to lose energy. It's an exothermic process. We just talked about this. So that means that I have higher energy to start than to end with. So I'm going to draw a curve that starts tall loses energy, and then ends lower. Okay? I'm going to label this as my high energy and low energy sections. Remember our kindergartner example? High energy kindergartners, are they stable? Do you want to be the one in charge of them after ice cream? Didn't think so. So high energy here is going to lead to low stability. Low energy down here is going to lead to high stability. Ooh, that was a horrible arrow. Don't forget that these guys are in an inverse relationship. Okay? You're going to have to write in the reactants and products. Do not just write the word reactant and the word product. That is a cop-out, and you are better than that. Okay? I'm going to grab a different color just so it pops a little bit. So our reactants, it's U-235 plus that neutron. Your products, it's krypton-91, barium-142, 3 neutrons. And I know that's very tiny handwriting to see. I promise I will do better on the next one. Okay. I'd like you to look at number 20 with me now, please. Portion of the binding energy graph is shown. This one shows the fission portion. So the last time we looked at mostly the fusion, this is fission. Or I'm sorry, other way around. Last time we looked at mostly the fission portion, this is fusion. All right, the first question wants you to notice the points on the graph where we find hydrogen and helium. Notice them now. Feel free to ooh and ah as needed. For part B, in a fusion reaction, when hydrogen fuses into helium, looks like this, 4 hydrogens fuse into 1 helium. Is your binding energy going to go up or down? So, and some of you are thinking, lady, I have no idea. That's okay because you can read a graph. We know that this section is more positive, this section is more negative. Okay? So as you move down this chart, are you going to gain energy or lose it? You're going to lose it. So if you're losing energy, is it increasing or decreasing? Well, it's decreasing. Let's go ahead and circle that one. This is exothermic. You knew it was coming. You knew I had to say it at least one more time. When hydrogen fuses into helium, does it absorb or release? Well, I just told you it's exothermic. You just told me it decreases, so this has to be releases. Look at 21. Loves, for 21, we're drawing an exothermic graph again. We might have just done this in 20, or I'm sorry, in 19. This is always when students ask me, wait, Francis, every single one of these we've drawn, the slope goes down. Can the slope even go up? Yeah. We're going to look at some reactions in the spring where we have to put energy in. The biggest one that y'all probably know that you have to put energy into to get something to come out of would be like digestion, right? We have to put a little energy in just to kickstart that reaction. However, with these just like couple of examples we've picked, they have all worked out to be exothermic, and that's okay. So let's go ahead. We're going to draw that L shape. Do you remember what the axes labels are? What are those axes labeled? One is energy and one is time. Take a second and guess which one's which. If you put energy here and time here, you are correct. The next thing I want you to do, because you totally do not need my help with this anymore, is label where the highest form of energy is going to be on the x-axis, or I'm sorry, on the y-axis, and where the lowest form of energy is going to be on that y-axis. I would do it off in this blank space to the right. Most of you know this without it even being like a science thing, that your higher energy is going to be on the top part and your lower energy is going to be on the bottom. Now think about your stability. Think about your kindergartners. Is high energy going to be high stability or low stability? These are in an inverse relationship. There's your hint from me. So if they're in an inverse relationship, when one goes up, what is the other one doing? Dance it out. You know the answer here. If you have that high energy is low stability and low energy is high stability, you are correct. Good job. The last thing we have to do when it comes to like the generic stuff is the actual drawing of this curve. So to do that, we are going to think about what it means to be exothermic. We know that this is exothermic. You told me in part C that this is releasing energy. You told me in part B that energy is decreasing. So that means that our slope has to show that. So I'm going to start with my like baseline energy amount, and then I'm going to lose some energy. I'm going to keep going. Normally I feel like my curves are a little more smooth than that. That one's got a little bit of an angle going on, but that's okay. The last thing we have to do is go in and label this. And I know you're thinking, Francis, I don't know how to label this. We have not studied this equation enough. You're right. I mean, it was an example in lesson 4, but that doesn't really mean that we've studied it. Luckily, we've got a little hint up here. This is the reactant. What is this if this is the reactant? This is the product. So our reactant goes first. So I know for my reactant, I have 4 hydrogen, 1. Okay, that means there's no neutrons. When this fusion occurs, we produce 1 helium 4. My 4 doesn't really stand out super well from my helium there. But those are the transitions we have. We do have 2 protons that turn into neutrons. It's a very complicated bit of physics as to what just happened. If you have this and this, that's all you need. Okay, that's all you need from me. So now we've got to look at 22 and 23. These are our summary questions. These are also key questions. So as a reminder, those are the important questions that we're going to look at. For number 22, how would the binding energy of various elements help us to explain why fission or fusion would make elements more stable? I want you to think about this for a second as I switch my pen color. What is happening here? As we undergo fission or fusion, what are we moving towards? I actually think that they do you a little bit of a disservice here because you can't see the whole graph. But when we think about the graph as a whole, right, it looks like a parabola doing yoga. It's tipped over. That curvature is important. Okay? We know that the binding energies explain fission or fusion because they are undergoing fission or fusion to reduce energy. So the elements are moving to a lower energy state. Okay. That lower energy state makes them more stable. So I'm going to add the words fission and fusion into my answer here just to bulk it up a little. Lower energy equals higher stability. Ta-da! All right. Question 23, I actually think also is on the slides, and if it's not, I'll put it there tomorrow because it's another one that's very like, how does a power plant work? Which we just didn't really spend a lot of time on. Basically, here's what I need you to know for this. Step 1. Mass gets converted to energy. And in parentheses, I'm going to put Einstein's equation just as a little reminder to myself. but that's what that does. That energy, specifically the form of heat, boils water. And I just put steam because the steam is going to be important here. Lovely. The steam, as you hopefully know by now, rises, right? If you've ever made mac and cheese on the stove, the steam does not sink to the bottom, it floats off. When that steam rises, it's going to spin a turbine. A turbine is essentially like a giant pinwheel that helps to make electricity. Okay? So steam spins a turbine. Creates energy. So much harder to write one-handed than I ever remember. Again, for me and in my course, I'm not asking you to know 23 beyond maybe this. Maybe. And I'm putting a maybe on it because I definitely expect you to know step 1. Step 2 and 3, I can live with it. Okay? A little star next to that. I was like, well, let's make it a really good star, though. I can't draw a star, you guys. Good enough. Okay. 1 is something we need to know. 2 and 3, I can live with the understanding wherever it's at. Because again, I don't care how a power plant works. What I care is that we know the physics and the chemistry here. So you need to know 1. 2 and 3, I can live without. Hopefully this video made this a little bit easier. I know for some of you, this was probably something that we felt confident taking on without me, but I also know that for some of us, that was not the case. And so I'm hoping that this just helps to make us feel a little bit more confident as we head into the weekend. I hope you have a great time at Collage. It's such a fun experience. I know some of you were at an engineering program today. I hope that was wonderful. And I can't wait to see you on Monday. Bye, y'all.